look at here is how we use data to get models. A lot of the times in mathematics we have a model, but in reality what we will end up with is data. So I'm going to use the Aldopa data from the homework assignment. And let's see, how much data do I want to use here? I think I will go out to 100. So I know the data continues further on the data sheet. But what we have is the L-DOPA levels measured in the bloodstream. Over time. And so, as a mathematician, or in whatever field you go into, when you use mathematics with data, you can make an assumption of a model, or you can see what your data is telling you the model should be. Now, if we plot this data, the full, we find that we start at 2,950, what is this, milligrams, nanograms per milliliter. And as we move through on time, this drops down. So we should recognize from the functions that we've seen that this is exponential decay. It is probably the best fit for the data. That we have an exponential decay when we plot this data. So we want to figure out how to fit. Now, exponential decay, we have our variable. I'll use the L-DOPA levels as a function of time. And the base model is there's some time zero value, e to the negative kt, because it's a decay model. Now, you don't have to put the negative sign here. If you don't have the negative sign, when you solve this for the data, your value for k will pick up the negative sign. But since we're seeing exponential decay and we're going to use this model based off of the graph that we're seeing. So that's the two things that we tend to do is we look at what the data is doing. This is decaying over time. And so exponential decay tends to be our best fit. So in general, with exponentials, the zero makes the exponential term 1. And we also know as a function, at time equals 0, this function is equal to 2,950 nanograms per milliliter. So we know that the initial value at time 0 is there. But by definition, we can grab that because we know this is our value at time 0. So what we want our data to tell us then is if we write what we know, that we have an initial model of 2,950 nanograms per milliliter, an initial amount, and that it's decaying over time. Well, time will be our independent variable. So the thing we need to find is k. We need to find the k constant. Now, there are many shorthand ways you can do this. When you solve for the k constant, the same pattern comes out. But let's work it through completely, and then we can point the pattern back out. So I'm going to pick time equals 100. That gets me far enough down the curve when I plot the data points that I'm sure to take in the bend on it. So we know that the function equals 725 at this time. There's our initial and e to the negative kt. So I've put my whole problem here to solve for k. So I'm going to isolate this part of the equation. So I'll divide 725 by 2,950. And now I have a raw exponential. And so we need to cancel this out, or we need to bring everything down from the exponent. And part of what we studied in the first chapter was manipulating exponents by using natural log. So I'll take the natural log of the ratio of my initial value and the value at the time I'm looking at. Oh, and I should say we're looking at this at time is 100, because we specifically put 100 in there. We're looking at 725, if we look back up the graph, was when t equals 100. Looking at this model when t equals 100. But if I take the natural log of one side, I take it to the other, and we know these are inverse functions of each other, and so the inverse function liberates what's upstairs. And if I isolate k, make a clear division sign here, negative 100. Now, some things we know about logarithms is that a small number, a number less than 1, which this fraction would be, gives me a negative log. So what's going to come out of this k constant is going to be positive. And there's a couple different ways we can focus on that. At this point, I would just plop the whole thing into the calculator at this point. And see the value that comes out of it. And so the value that comes out of it, we get k is equal to 0.0140339. Now, I'm going to keep all these extra decimal places for my model. I think within the precision we have, that's 4 significant figures is probably okay, but I'll keep it at 6 for right now. And so the model that I'm able to make from this t pushes the whole change function and how the rate of change is going through into the k constant. And so the k constant comes through. Now, the thing to notice, and when I taught rad tech students who had to remember half-lives, so they always knew what the half-life was in years, which meant that this natural log was always the natural log of 1/2, which would always answer a certain way. And this bottom number would be whatever the time you were given for the half-life to be. And so you can kind of note that the top part's going to be the amount you have at the time. The bottom part's your initial amount. And then this is the time frame that it takes to arrive to these points. So you could, if you work with these enough, always go right to k. But that's a steep memorization ask and works for some very specific things relatively easily. So the manipulation of using the natural log helps. And this is kind of realistically a lot of how mathematics is used. We might think exponential models are driving things, but the details of that model come directly from the data. And so this is how we would approach if we saw an exponential decay in data, how we would take the data to create our model.